Welcome to the lectures on modern digital communication techniques. So, after discussing about transmission techniques and the receivers where we could detect the signals, we are now discussing the performance of digital communication systems or digital modulation techniques, and we are evaluating the performance by means of error probability. And we have explained on several occasions why this error probability is significant. And just to remind, the importance comes because the receiver has to make a decision between a few options. So, the receiver cannot make any choice which is lying outside the set of options. Accordingly, the decision made by the receiver could be the exact signal or the exact waveform that was sent, or it could be some other waveform, and hence we have the issue of whether there is a mistake in detection or whether it is a correct detection. And accordingly, we would like to calculate the chance of making an error. The lesser the chance of making an error, the better is the performance of the communication system. We have studied the error probability of binary pulse amplitude modulation, and we have extended the concept to the study of M-ary pulse amplitude modulation. And what we have found is that as we increase the order of modulation, that means as we increase the size of the constellation, we are getting a decrease in the performance, in the sense that for a given finite amount of energy or average power of the signal, as we increase the m, that is the order of constellation, we are getting a decrease in an increase in error probability. So, what we have also seen, there is a trade off between the bit rate and error probability in case of modulation such as pulse amplitude modulation. What we have seen is, if we fix the symbol duration, that is t, and increase the k, which is bits per symbol, then effectively the number of bits sent per symbol duration, that is per unit time, keeps on increasing, that is k upon ts, which is bits per second, keeps on increasing. Whereas, for the same situation, if we keep the average energy constant, that means we are not spending extra power compared to the earlier situation where k was a lower value, that means we have increased k, but kept the average transmit power the same. In that case, what we found is that probability of error increases. So, there is an increase in bit rate as well as increase in error probability. Now, if we have to maintain a certain quality of service, that means if you have to maintain error probability below a certain threshold, then as we increase the number of bits per symbol duration, that means as we increase the modulation order, we should also increase the transmit power in order to maintain the same probability of error. So, that was visible in a curve like this. So, in this particular picture, we not only had PAM, but we also had QAM, and we said the performance is very similar, simply because QAM can be constructed by two PAMs. So, what we find is m equals to 4 and m equals to 16, m equals to 4 for PAM has similar performance as m equals to 16 for QAM. The reason being, 16 QAM can be constructed by 4 PAM. So, if this is 4 PAM, you have another 4 PAM, and we had reminded you that this could be used to construct a 16 QAM, and whenever a signal is received, suppose a signal is received here, its component is taken on the I PAM as well as its component is taken on the Q PAM. So, once its component is taken on the I PAM, then you can find the appropriate PAM signal on the I channel, and you can also do the same on the Q channel, and accordingly we derived the error probability for QAM. So, after having discussed this particular modulation scheme, the performance of PAM or QAM, which is multi amplitude signal, we would like to look at the next important digital modulation technique which we have studied are the ones which use orthogonal signals. Now, what we have studied for orthogonal signals, if you would recall, that one way of creating such a signal was, if you have a bandwidth, you would divide it into orthogonal sections, where each sub bandwidth would be of size delta f, and if the symbol duration was of period t, then if you would maintain delta f is equal to 1 upon t, in that case these frequencies would be orthogonal to each other. That is what we have found. So, by this we could create n dimensional orthogonal signals, and whenever we are discussing the performance of orthogonal signaling, one could easily consider this as a possible realization in trying to connect to the outcomes that we get. So, moving further, so we are now interested in calculating the probability of error for M-ary orthogonal signals. So, in study of the M-ary orthogonal signals, we will take a look at the optimum detector. So, we have discussed what is meant by the optimum detector and how it is realized. So, there are several realizations, and one of the realization, as we saw while expanding the expression. So, just to remind, we started off with the posterior probabilities, and what we found is that it could be expanded using Bayes rule, where the denominator term did not influence the decision, and in the numerator term there was the multiplication of the likelihood function by the prior probabilities. If prior probabilities are equal, then it turned out to be the maximum likelihood detector. In such a case, we found the way to find the possible signal was the minimum distance detector. Then we expanded this particular metric, and what we found it expands into the expression of the length of the received vector, along with that component of the received vector on the different signals, as well as there was the bias term of that particular signal's energy. So, when we consider this particular expression, we looked at it and found that the length squared of the received signal is common for all comparisons, hence we removed it, and we were left with is the correlation of the received signal with the different signals. And the realization was correlation of the received signal with a particular one of the signal waveforms, take away the energy of that particular signal. So, effectively what we had was the correlation. Now, if we have the M-ary orthogonal signals, and if you recall this particular structure, or even if you recall the situation where there was a long time duration t and one could use orthogonal time slots, and each time slot had the same energy. So, in this case our signals were as if is the vector, and finally, so that means they had the same energy, but they had only one component and the rest of them was 0. So, that means they are all equal energy, and at that point we said that if mod Sm squared is same, that means all of them have same energy, then we need not take this term and we could easily concentrate on r dot Sm, that is the component of r on Sm, or we could take r of t Sm of t 0 to t dt, that is the correlation of r on Sm t, and we would select that m, this or n, because we had used both these things to mean the same. So, whichever value of small m would maximize this correlation was the choice of the signal, that is what we said. So, it could be implemented in either of these two forms. So, in case of equal energy signals, we would select the signal, that is Sm, with the maximum correlation with r, that is what we just explained in this particular short discussion. So, we would compute the correlation matrix, the correlation metric, and the correlation metric is what we have just stated. So, in the vector form, the correlation metric is the product of the kth component of the received vector. So, we are taking the component on the basis dimensions. So, getting back here, each of them are basis functions. So, whatever is the received signal, we will take a component of each one. So, the received r of t would be broken into r k times f k t, k equals 1 to M or N, either thing in this case, it is the same in this particular situation. Same applies in this way or any other constellation which may make sense. So, M is the index for the signals waveforms and K is the index of the basis function. So, that is what we have. So, now, so this is a generic expression. Okay. To evaluate the probability of error for S1. So, we are assuming that there is the S1 that is being sent, that means we are assuming any one sent. So, it will be the same for all others. So, it is not much of a problem. So, let us consider with S1, and this is the approach we had taken while discussing the performance of PAM signals as well. So, to evaluate the probability of error for S1, let us consider the received vector. So, it will naturally be the signal plus noise in the first dimension, because there is signal already present in the first dimension, and in the other dimensions there are no signals. So, output of the correlators will be the noise component on the basis function. So, that is again straight ahead available from this, because you are first decomposing R onto the different components. So, you are basically taking R of t f k t integrate 0 to t dt, and R t was S m t plus n t. This exercise we had done thoroughly before, right, and hence what you have is S m k integral 0 to t S m f k, and you had n k, right, that is the component of noise on the basis dimension. So, this is what we had, but that is what we are using. So, for the first dimension there is signal. So, there is the signal component which is root over E s, and on the other dimensions is just the component of noise that fills the R vector. And of course, need not mention over here, E s is the energy of the signal. If you square this term, you are going to get energy of the signal, and noise power spectral density or the variance of noise is n naught by 2, which is consistent with all our previous discussions. So, now let us take a look at what would be correlation output, correlator output of the first correlator. So, if we look at the first correlator, the signal is root over E s, right, S1, and this is the R component on the first dimension. So, this is the correlator output. The correlator output of the second correlator is R times S2. So, R has a component N2 and signal S2 is Es on that particular dimension, and similarly we are going to have this. So, if you look at this expression, all of them has this particular thing common, and hence we can divide by root over Es, and then we are left with basically these components. Then the normalized PDF of the first correlator output, that is what you have over here, is given by PR1, that means component on the first one, let x be that variable, 1 by root pi n naught, because sigma squared n is n naught by 2, there was a 2 pi sigma squared n, 2 and 2 cancels, and e to the power of minus x1 minus root E0 Es, because this is the mean of the signal, and this is the Gaussian distribution with variance of n naught by 2. This we have been using before. For all other correlators, what you can easily see that the normalized PDF should have a mean of 0, the normalized output should have a mean of 0, and the variance will again be n naught by 2. We are ignoring this term because it is common to all. So, we can divide by root over E s and we can eliminate that term. So, we write P R M. Now, we are using the M because for our particular case it is M and N are same. So, therefore, this is the situation. So, x m is the general symbol, this is the root 2 pi sigma squared e to the power of minus x m squared by n naught, because these do not have a mean, this is basically the 0 mean for all other correlator output. So, now we have to use this to calculate the probability of error. So, in order to calculate the probability of error, it is better in this particular situation to go ahead with calculating the probability of correct decision. So, the probability of correct decision is the probability, the joint probability that N2, that is the second component, is less than the first component of the received signal, the third is greater than the first component, and simultaneously up to all components are less than the first component given R1. and this has to be averaged over all possible realizations of R1. So, accordingly the integration range of R1 minus infinity to plus infinity, right. So, this is averaged over all possible R1, and now since we have always been using that if these are orthogonal signals, so we have been using them to be orthogonal, let us say. So, if they are orthogonal, then if they are orthogonal, in that case RMs are statistically independent, because they are Gaussian distributed and first one has a mean of root S, all others have mean of 0. So, if they are orthogonal and Gaussian, that means they are statistically independent. So, statistically independent means that this joint distribution, of course conditional, turns out to be a product of the individual or the marginal distributions, of course conditional, for all the m terms from 2 to m, right. So, where any individual marginal PDF, condition marginal PDF is obtained in this fashion as written over here. So, which is simply, so it is minus infinity to R1, because you want this variable to be less than R1. So, minus infinity to R1. So, this should range from minus infinity to R1, P of xm conditioned on R1, right. So, that is what you have over here, and that turns out to be minus infinity to this range with change of variables. So, this is the expression for any particular other PDF, and it is same for all. It is simply same for all, and you can easily guess by looking at these correlation outputs. All of them have a similar output. So, it is the same PDF, and hence the probability of correct decision, which we have written over here, can now be written as the individual raised to the power of m minus 1, because we have 2 to m. The first one is of course the 1 itself. So, for all others must be less than the first component. So, this joint distribution becomes a product. So, that is what we have over here in this particular expression, and then in order to calculate the probability of error, it is simply P probability of error is 1 minus probability of making correct decision. So, hence probability of making a correct decision is 1 minus P c, which is this whole expression, which you can easily see. Okay. So, 1 minus this, and it is averaged. So, this is the average probability of expression, average probability of error, which is given by 1 by root 2 pi e to the power of this particular expression as we have. So, it is averaged over all possible values of r, and that is what is the expression, here it is. So, this expression is cumbersome, and it has to be solved almost numerically in most of the cases, other than very simplistic situations. So, what we will do in this particular case is, instead of calculating the exact expression of error, we will use the results which can be found by solving this particular expression, and will focus on the performance of such scheme, that is error probability versus the EB by N naught, or the signal to noise ratio. So, for equiprobable signals, we could write P m upon m minus 1, which is equal to P m upon 2 to the power of k minus 1, that is m is equal to 2 to the power of k, and there are choose n out of k bits. That means, since there are k is equal to log base 2 of m, so each symbol duration consists of k bits, right. So, all what we are trying to do is, a symbol can go into error by 1 bit going into error, or 2 bits going into error, or 3 bits going into error, or 4 bits going into error. So, because these are, if you look at it, just try to, it is a bit difficult to imagine. Suppose we have constellation points which are these. So, this signal, if it is sent, could go into error if the correlation on this dimension is less than the correlation on other dimensions, and the correlation on any of these dimensions have equal probability to be better than this or to be less than this. So, they are not differentiated, and that can be again understood from what we have over here. If you look at these are very, very similar. It can also be understood based on this, because if we have sent S1, what we receive is, if S1 is sent, what you receive is root E plus N1 at the output, N2, N3 up to Nm. This is what we have said. So, now probability of this being greater than this is similar to the probability of this being greater than this, and so on and so forth. So, what it means is that all these signals are equidistant from each other, right, and because of equiprobability we have this situation. Now, why we are discussing this? The reason is that in the other scenario where we had PAM, so let us take a few more constellation points. Okay. So, we have 8, although it is not equispaced. So, if we were choosing this particular symbol, let us say we are transmitting this symbol, then we said that the conditional PDF goes like this. That means, given that you have sent this symbol, probability of the received signal lying in this range is area under this curve, which is pretty large. Probability of this signal lying, let us say, in this range is much smaller compared to probability of the signal lying in this decision interval, right. So, that means probability of probability of this signal being detected as this is even less, because the PDF falls, area under this curve is even less, right. So, what we mean to say is that if I have sent this signal, the highest probability for this signal is probably to remain over here, and if at all it has to go into error, it has a higher chance of going to the neighbor, and going to the neighbor far away is even less. So, going to this neighbor is probably equal to going to this neighbor, but being decided at this neighbor is much less than probability of becoming this neighbor. Now, probability of becoming any of the neighbors is generally less than probability of remaining by itself. So, that is how we design communication systems. So, that and remember, we had considered gray coding. That means, if one makes a mistake by going into the neighboring symbol, there is at most 1 bit error. So, that means, probability of making 1 bit error is much more than probability of making 2 bits error, than probability of making 3 bits error, and so on and so forth, right. Whereas, in this case, since the constellation points are such that if I would consider n dimension, this is not n dimension, this is just imaginative, if these are all orthogonal and they are equidistant, then this symbol could be detected with equal probability on all the orthogonal dimensions. So, that means, there is the probability of getting 1 bit changed is the same of probability of getting 2 bits changed, and the probability of getting all bits changed. So, anyway, but the symbol can get into error by 1 bit going into error or all combinations of different bits going into error. So, we have to take out of k bits, n possible bits can go into error, is the number of ways it can go into error is k choose n, that is a combinatorial. Okay. So, this is what we have, and since 1 bit can go into error, with 2 bits can go into error, and 3 bits can go into error. So, it would take up all such possibilities, right. We have to take all such possibilities along with the possibility that any of the bit goes into error. So, by expansion of this term, what we have is P m upon m upon 2 to the power of k, because as k is greater and greater than 1, then this is almost equal to 2 to the power of k. So, you could solve this with this approximation, and you could get that probability of a bit going into error, would be approximately equal to probability of a symbol going into error by 2. So, this is an approximation that you can reach to, but this is just translating the symbol error to bit error probability. So, using that and the solution of this expression, numerical solution of this expression with E b by n naught. So, what we can have is the probability of error curves versus EB by N naught, okay, is what we have plotted over here, and it might be quite interesting to look at this particular result. So, what we have with us here is this line, this particular curve, which is the probability of error for m equals to 2. That means, you have only 2 signals to choose from, right. Whereas, when m is equal to 4, what we find is that the curve is changing in the left side direction. That means, it is going towards the left. Whereas, you might remember when we discussed probability of error for PAM like signals, we had a situation which was here. That means, as m increased, you are going to the right, whereas in this case, as m increases, you are going to the left. So, we have not done anything, simply by solving that error probability expression, and as a function of EB by N naught, you generate this curve. It might be quite surprising that why we have this kind of a result, and unfortunately, by looking at the expression that we have here, it might not be feasible to straight away comment that why such a thing happens. So, it might be we might address it in a few different ways, and one of the ways generally as is addressed in the literature is through the union bound. However, we can take and try and take an intuitive view of why such a thing happens, to get a feeling of, well, this could be a possible reason, to remember the basics. However, the union bound and what we do afterwards would give a concrete impact of explaining why do we have this kind of a behavior. So, let us briefly look at some of the things here. So, what we stated here is, as m increases, we find that as m increases, as you increase m, right, the EB by N naught decreases for the same PB. That means, if I keep a particular probability of error, right. So, as I increase m, so I go from this m to this m and this m to this m. So, basically, as I go there, right. So, or as I increase m, with keeping the same PB, I am changing from m equals to 2 to m equals to 4 to m equals to 64. What I find that the EB by N naught that is required, so we should write required, decreases, right, as m increases. So, quite contrary to what we have seen there. So, generally the question that we have just discussed is, why should this happen, that why at all this should happen, right. And the next question that we can ask, that as we keep increasing m, what is the, where is the limit of the curve? Does it reach a limit, or we keep on going below, is the next important question that we are confronted with. So, in the next lecture, we will try to address this particular issue of orthogonal signals, where one of the realizations could be M-ary FSK. Thank you.